तब तक भेजना ताकि मम्मी का
Rathod sir, good morning.
Good morning, sir. Good morning. How are you?
Bas, fine.
Pallavi madam,
Yes, sir.
let's start. Start.
Okay, sir. Okay. A very good morning to all of you. I, Pallavi Thakkar, welcome one and all present here of Organizing Committee at Bharatiya Vidya Bhavan's Sardar Patel Institute of Technology. I take this privilege to warmly welcome you all on this seventh day of AICTE sponsored 2-week online faculty development program on insights into intelligent automation, machine learning, and data science, and under the theme Artificial Intelligence and Machine Learning. I find immense pleasure to welcome Dr. Priyank Thakkar. Dr. Priyank Thakkar is working as an associate professor in the Computer Science and Engineering Department at Institute of Technology, Nirma University, Ahmedabad. He has more than 18 years of experience. He has done PhD from Nirma University. He has published many research papers in international journals and conferences. At present, Sir is working on 2 funded research projects and also guiding 5 PhD students. He has served as program committee member of many international conferences. He is a reviewer of several international journals. His research interests include data and web mining, machine learning, soft computing, deep learning, and their applications. Once again, I welcome you, sir. Now, may I request, sir, to take over the session, please?
Yeah, thanks a lot, Pallavi ma'am, for the introduction. I hope I am audible properly. Hello.
Yes, sir. Yes, sir,
Uh,
you are audible.
Thanks a lot for the introduction. So, yeah, so now I'll be sharing my screen. I hope the screen is visible now.
Yes, please go ahead.
And Dr. Surendra, I have personally messaged you my mobile number. I don't know whether we have each other's mobile number or not.
Yeah, I have, sir. I have. I got you.
Yeah, in case if something goes wrong, you know that
Yeah.
network, computer network sometimes it doesn't go well. So in case if something goes wrong, you have my mobile number as well.
Yeah, I'll call.
Yeah. Yeah. So very good morning to one and all present here. So I'm supposed to discuss regarding solutions to non-linear problems using artificial neural network and backpropagation. So basically, there are two things which I would be discussing. And the outline of the discussion would be like this. I'll be starting with basics of artificial neural network. So I'll quickly go through basics of artificial neural network. Then we will see that how you can use ANN to solve linearly separable problem. Then we will see that how we can solve linearly inseparable problems using ANN. So basically non-linear problems. How we can solve non-linear problems using ANN. So that we would see in the second part of my discussion. And towards the end, I'll discuss the backpropagation algorithm. I think all of you know that it uses gradient descent. So we will also discuss that. So basically, there would be three sections in which we would be discussing this. First section, I'll introduce ANN. In the second section, we will see that how we can use ANN to solve linearly separable and linearly inseparable problems. And in the third section, we will look at the backpropagation algorithm, error backpropagation algorithm. So we will see the derivation of that. So this is the whole idea for the presentation. And what I'll do means after every 10-15 minutes, I'll break for a minute and will invite your questions. You know that interacting in the online mode is slightly difficult, but that's the way I conduct the lecture for our students as well. It's like every 10-15 minutes, I break and invite queries. So we will do that. But in case if you want to ask in between, you are welcome. Yeah. Yeah, so first thing is, as I told you that I'll be introducing artificial neural network. So my first question is, what is artificial neural network? So that is what we need to understand, that what is exactly artificial neural network. So if you want to define artificial neural network, in the simplest term, I can say that artificial neural network, they are computing systems inspired by biological neural networks. Please remember, I said that ANNs, artificial neural networks, are computing systems inspired by biological neural networks. So they are nothing more than computing systems, but they are inspired by biological neural networks. The computation which takes place in artificial neural networks is actually inspired by the computation which takes place in biological neural networks. So all of us have nervous system, and part of that nervous system we have biological neural networks. So our biological neural networks is actually made of biological neurons. So we need to have a bit of understanding regarding biological neurons, because later on I'll be introducing artificial neuron and artificial neural network. So you need to have a bit of understanding about biological neurons and biological neural network. And I'm saying that AN, artificial neuron, and ANN, artificial neural networks, are inspired by BN, biological neuron, and biological neural network. So you should be able to see that resemblance. I'll discuss a bit about biological neuron and biological neural network. Then you should be able to figure out the analogy. So that is what is my objective. I'll present them, and then I'll try to see that you can see the analogy between BN and AN and BNN and ANN. So I just said that ANNs are computing systems inspired by biological neural networks, and all of us have biological neural networks, and our biological neural networks is made of billions of neurons. So please mind this. I say that our biological neural networks, they are made of billions of biological neurons. So now what do I mean by biological neuron? So from ANN, I went to BNN. I said that ANN is inspired by BNN. Then I said that BNN consists of billions of biological neurons. So now I think it's time to understand what is biological neuron. So if I want to define biological neuron, then I can say that biological neuron is electrically excitable cell. Please mind the words. I'm saying that biological neuron is electrically excitable cell which can receive amplified or attenuated information from multiple sources, can aggregate this information, can process this aggregated information, and can produce the output in terms of electrical and chemical signals. So this is what is biological neuron. One more time, I say that biological neuron is electrically excitable cell. So it is electrically excitable cell which can get excited through electrical signals. So it is electrically excitable cell which can receive amplified or attenuated signals or information from multiple sources. So you can see that it can receive information from multiple sources, and this can be attenuated or amplified while receiving. So it can receive amplified or attenuated information from multiple sources. Then it can aggregate this information which it is receiving from multiple sources. Then it can process this aggregated information and then produce the output in terms of electrical and chemical signals. So this is a kind of biological neuron. Right now you can see this. So this is actually biological neuron. This is this one. You follow the cursor. This one is the cell body. I said that artificial neuron is an electrically excitable cell. So this is the cell body. Within the cell body, you have a nucleus. So nucleus is like a processor. Nucleus is like a processor. This processor is though not very powerful, but this nucleus is a processor within the body. This, this hair-like structure you can see, which is attached to body, is actually they are actually dendrites. These are actually dendrites, and dendrites are like input channels to the artificial neuron. These are actually dendrites, and they are like input channels to artificial neurons. So if you remember, I told you that it can receive inputs, it can receive information from multiple sources, and therefore you can see quite a few dendrites. Therefore, you can see quite a few dendrites. So it can receive information from all these dendrites. Then it can aggregate this information which is received from multiple dendrites into aggregated information. This nucleus can process aggregated information and can produce output on axon. So axon is like an output channel. Axon is like an output channel. It is thin tube-like structure. If you can see carefully, it's actually thin tube-like structure. So this is actually an output channel. So please be mindful. I said that these are input channels. They are known as dendrites. The axon is the output channel, and aggregated information is processed by the nucleus, and the process information is output on axon. On the other end, axon is divided into multiple branches. Each branch is ending with blob-like structure. And if you can see this, these are dendrites of other biological neurons. So this is one biological neuron. I told you that biological neural networks, they have billions of biological neurons. So these are dendrites of other biological neurons. So this information, the process information, which is traveling over axon, then can transferred to this dendrites, and then other neurons can receive this process information. So these are actually dendrites. And this is synapse, or this is a synaptic gap. This is synapse or synaptic gap. And over here, your information can get amplified or attenuated. So this is the basic detail. I'm not going into a lot of detail, but what you need to notice is that there are input channels which are known as dendrites. Means it can receive information from multiple sources. Then it can aggregate this information. It can process the aggregated information and can produce the output which can be received by other biological neurons through their dendrites. Through their dendrites. So this is what you need to remember. Why am I saying that you need to remember this? Is because if you can recall, I told you that I'll set up the analogy between biological neuron and artificial neuron. So now you know the characteristics of biological neuron. So artificial neuron should have these characteristics as well. I'll be presenting a model of artificial neuron, and it would be modeling biological neuron. So the characteristics which are there in biological neuron should also be there in artificial neuron. So therefore, you please remember these important characteristics. And now some more facts. So we have biological neural networks which consist of biological neurons, and there are 10 to 100 billion biological neurons. So we have 10 to 100 billion biological neurons. See, each neuron is connected to 100 to 10,000 other neurons. So please imagine the complexity of the network which we are having within our body. We have 10 to 100 billion neurons. So they are like nodes of a graph, nodes of a network. We have 10 to 100 billion neurons. Each neuron is connected to 100 to 10,000 other neurons. So number of connections you can imagine. So many connections and kind of complex network we are having. And therefore we are able to accomplish tasks which are still difficult for computers to accomplish. We can do face recognition very easily. We can do language translation very easily. Many natural language processing tasks and computer vision tasks we can do very easily. Uh, Even though there is a lot of advancement because of deep learning in computer vision and natural language processing, but still, we still for most of the problem, it is not able to match human performance. So we are able to do this because of this. We have 10 to 100 billion neurons. You know that each neuron has a nucleus, which is actually a processor. So you can say that we have almost 10 to 100 billion processors. Each processor is very simple, not very powerful, but the key is that we have 10 to 100 billion simple processors. When they work together, they can accomplish any complex task. Also, this 10 to 100 billion neurons are not of the same type. There are almost 100 different types of the biological neuron, and they are not arranged randomly. Rather, they are arranged into layered structure. So this 10 to 100 billion neurons, they are not arranged randomly. They are actually arranged into layered structure. So these are some more facts about biological neurons and biological neural net. Now, keeping this in mind, I am presenting you artificial neuron, which is actually model of biological neuron. I am presenting you artificial neuron, which is actually model of biological neuron. So let us recall that biological neuron is able to receive the amplified or attenuated inputs from multiple dendrites. So this was the characteristics in biological neuron. I am recalling this because AN artificial neuron is a model of biological neuron, so it should also have these characteristics. Then it is able to combine these inputs into aggregated input. Then it is able to process input and produce output. These are three major characteristics of biological neuron. And now this is artificial neuron, which is a model of a biological neuron. This is artificial neuron, which is a model of a biological neuron. So please have a look at this artificial neuron carefully. So this is an input. This is an input. So this is a one-dimensional input. This is another input. This is known as special input. I am not discussing why it is known as special input right now, but this is another input. So you can see that one input is P. So P can be any scalar quantity. P can be any scalar value. This can be, let's say, height of the student, or let's say this can be weight of the student. So this is problem dependent, but P is basically input. P is basically 1D input. So this is one input. This is another input, which is a special input. And see, so already you can see multiple inputs. Please recall, biological neuron is able to receive the amplified or diminished inputs from multiple dendrites. So it can receive multiple inputs. So already one input is P and another input is 1. Already one input is P and another input is 1. So multiple input. And you can see this is the connection or the age. And this connection is not simple connection. This is weighted connection. This is weighted connection. So let's say weight of this connection we are denoting as W, and weight of this connection we are denoting as B. So W stands for weight and B stands for bias. This stands for bias and this stands for weight. So W is the weight of this connection and B is the weight of this connection. So P is one input, one is another input. When it reaches to sigma, when P reaches to sigma, it is no longer P, rather it is P into W. Actually, there is something called weight function that defines that how weight value and input are combined. So typically weight function is a product function. So therefore your input and your weight is typically combined by means of a product operation, multiplication operation. So when P reaches to sigma, it is not P, but it is P into W. It reaches to sigma as P into W. So let's say P is 5 and W is 2. Then when the signal reaches to sigma, it would be 5 into 2 means 10. Similarly, when 1 reaches to sigma, it would be 1 into B. It would be 1 into B. 1 into B means B only. So basically sigma receives W into P plus B. Sigma receives W into P plus B. It receives two products, 1 into B and P into W. And see, I've just discussed weight function. So weight function actually defines that how your weight and inputs are combined. So I said that typical weight function is a product function, multiplication function. So input P and is multiplied with weight W when it reaches to sigma. So P into W reaches to sigma. Similarly, 1 into B means B reaches to sigma. Next is net input function. How you aggregate different inputs. So you aggregate different inputs by means of a sigma, sum operation. You are receiving as such products. So you apply sum on it. So basically you are calculating sum of products. So over here, W into P is received and B is received. You perform sigma on it, you perform sum on it. So you know that this N, which is the output of sigma, is WP plus B. This is known as net input. output of net input function, which is sum, is known as net input, which is WP plus B. So we have discussed weight function, we have discussed net input function, and then you have transfer function. The transfer function is also known as activation function. More popular name is activation function. So transfer function or activation function. So next is transfer function or activation function. So basically, this function is applied on this input, and you produce the output, which is known as actual output A, which is known as actual output A. So f of n, you apply f on n, net input. So f of n is actually A. So A is basically f of net input. And you know that net input is WP plus B. So this is actually WP plus B, because N is WP plus. So A is this. A equals to F of WP plus B. So this is the model of artificial neuron. Now you should not accept it without understanding that these important characteristics of biological neuron are mapped over here. So let us check it out. The first characteristic was BN is able to receive the amplified or diminished inputs from multiple dendrites. That is, it can receive information from multiple sources, amplified or attenuated information from multiple sources. So you can see that it is receiving information from here as well as here, and you can see that based on the value of W and B, while it reaches to sigma, it can get amplified or attenuated. So it's like if W is less than 1, then it would be, and P is positive, then P into W would be lesser than P. And if W is greater than 1 and P is positive, it reaches to sigma as P into W, and P into W would be greater than P. So basically W and B controls when P and 1 reaches to sigma, whether they are amplified or attenuated. That is controlled by W and B. So multiple information from multiple sources, and amplification or attenuation controlled by W and B. You can see that the first characteristic is model. The second characteristic is it is able to combine these inputs. So you can see that WP plus B we are combining by means of sum operation. So even second characteristic is modeled. Now the third characteristic is it is able to produce input. It is able to process input and produce output. So this is your net input. So you are processing net input by means of F, and F of n is your output. So it is able to produce the output by processing net input through some activation or transfer function F. So even the third characteristic is model. So now you can see that all three characteristics are model, and therefore we should be fine to accept this as the model of biological neuron. So this is artificial neuron, and you can see that it has modeled all three important characteristics of biological neuron. So in simpler words, artificial neuron is simply this equation, or it is simply this mathematical function. Artificial neuron is simply this equation or simply this mathematical function. So P is your one input, B into 1 or B, whatever you write. So if you write this as B into 1, 1 is your another input. B and W are taking care of amplification and attenuation. Plus is taking care of aggregation of information from multiple sources. And F, uh, which is an activation function, it processes net input by means of whatever it is. So F can be a linear function, F can be a sigmoid function, F can be any other function, F can be any other function. So there are quite a few options to have uh, some popular functions as activation function. So your artificial neuron is actually this mathematical function. So I have just introduced model of biological neuron, or in other words, I have just introduced artificial neuron, and I have modeled all three characteristics of biological neuron in artificial neuron. Yeah, now before I proceed, if there is any doubt, participant can unmute and ask, or they can write their query in the chat window. I have overlaid the chat window over here, so I can see your query if you post in chat window as well, or you can unmute and ask. So I'm waiting for a minute for a query. If there is no query, I'll proceed. I think I have a query from Manoj. How to decide type of F to use? So I say that there are many popular activation functions. So first of all, and your query is how to decide which F to be used. So Manoj, there are quite a few ways actually. First is that F would determine the nature of your output. F would determine nature of your output. So if you are solving a regression problem, if you are solving a regression problem, you know that your output should be continuous value. So F can be a linear function. F can be a linear function. And if let's say you are solving a classification problem, and let's say binary classification problem, then F can be a log sigmoid or 10 sigmoid function, because you know that if I don't know whether you know this or not, but if F is log sigmoid, then the output would be between 0 and 1. It is guaranteed that the output would be between 0 and 1. And then what you can do, you can threshold at 0.5. So less than 0.5, one class, and greater than 0.5 to 1, another class. So it depends, first of all, it depends on the type of problem you are solving. And sometimes, let's say you know that you are solving classification problem, then whether to use log sigmoid or 10 sigmoid, because log sigmoid will output between 0 to 1, and 10 sigmoid will output between -1 to 1. So if it is outputting between -1 to 1, you can threshold at 0. So sometimes both may work, or sometimes experimentally you need to decide that which works well for your data and your problem. So it's actually a hyperparameter. See, any machine learning model has set of hyperparameters. So which activation function to be used, which transfer function to be used, first you use your domain knowledge and decide that, okay, these are some possible options. And then if all of them are applicable for your data and your problem, then you need to figure out by means of tuning the hyperparameter. So for hyperparameter tuning, many popular algorithms are available, and one of the most popular algorithms is the grid search algorithm. So you may use some algorithm like grid search. Yeah, any other question? Yeah, I think there is no question apart from this. So let me proceed. So I have presented you the model of artificial, or I have presented you artificial neuron, which is a model of biological neuron. So there was one input P and another input 1. But if you remember, I told you that this is a special input. So actual input is only 1D. Actual input is only 1. You may say that I want to give, more than 1D actual inputs. It's like you want to give height and weight of the student as an input. So that's not possible over here, because P is a scalar quantity. And another input is a special input 1. You cannot change this. This has to be 1. So now let's say you want to give height and weight of the student as an input. Then P, I told you, is a scalar quantity. Then you can do something like this. You can do something like this. So there you can see that you have P1 to PR. You have P1 to PR. So it's like it supports R dimensional input. It supports R dimensional input, and R can be any positive integer. It supports R dimensional input, and R can be any positive integer. So if R is 5, means P1 to P5, means it can take a 5-dimensional input. So you look at your data, you look at the dimensionality of your input, and then decide that what should be the value of R. If your input is 3-dimensional, then P1, P2, P3 would be fine. If your input is 10-dimensional, P1 to P10 would be required. So artificial neuron suppose multiple actual inputs as well. So P1 to PR. And again, you know this sigma, you know this F, but now because there are multiple dimensions, so it's like, let's say we have P1 and P2 only. Let's say our input is only 2-dimensional. Then we will not have P3 to PR. We will just have P1, P2. So P1 may be, let's say, height of the student. P2, let's say, maybe weight of the student. So they will propagate on distinct ages. They will propagate to sigma on distinct ages. So like over here, this age will have some weight. Similarly, this age will have some weight, and this weight would be different than this weight of this age. Weight of this age would be different than weight of this age. So each dimension of the input will propagate on distinct age, distinct connection. and each connection can certainly have a different strength or different weight. So like over here, weight of this connection is denoted as W11. See, over here the notation is like this. In the subscript, the first number is the neuron number and second number is the input dimension number. So we have just one neuron. So this is one, and see this age is carrying first dimension of the input, so W11. If you focus on this second one, then you know that again it is carrying input to first neuron, so W1, but it is carrying second dimension of the input, so W1, 2. So means I have taken this from MATLAB toolbox. So in MATLAB toolbox, they follow this notations. So first is the neuron number, and the second is the input dimension number. But these notations are not consistent. These notations are not consistent. Different literature use different notations. Means in some cases, the first number would be the input dimension number, and second number would be the neuron number to which the information is propagating. So that's fine, means even in my slides later on you will find other way around, but I'll clarify that explicitly. But over here it is like this. So if let's say if I talk about P3, then this is the age which is carrying P3 in case if we have third dimension as well. Then the weight of this connection is designated as W1 because it is carrying to first neuron. There is only one neuron in this figure, and it is carrying third dimension, so W1, 3. And this W11, W12, W13 would be some scalar value. Would be some scalar value. So in that way, this would be W1R. So you can understand sigma. What would be sigma or what would be net input? So P1 is propagating on this whose strength is W11. So P1 into W11, you can see that W11 into P1 plus this is W12 into P2 plus W13 into P3. So you can see that, and then W1R into PR, and then 1 into B means B. So this would be the net input, which you process through F, which you process through F.
Excuse me, sir. Can I ask one question?
Yes, yes.
Sir, actually, any real-time example can we have it for this same thing?
What sort of real-time
Real-time
example?
example. Any example if you are giving, then it will be more clear, this concept. The
So
activation function, everything we are
it's
having,
very
but any real-time small model, anything.
it's very early to do that, but still I'm helping you out. So let's say you want to learn artificial neural network, which will take student as an input and will predict whether the student is obese or not. Did you understand the problem? I'm saying that you want to
Yes,
build
sir.
an
Yes, sir.
artificial network which will take student as an input and will predict whether the student is obese or not. Okay. So student as an input means height and weight of the student, because you know that to decide whether the student is obese or not, which two features are important? Height of the student and weight of the student. Am I right? So in that case, your P1 would be height of the student and P2 would be weight of the student. And then you will calculate N.
Okay, sir. Got it, sir. Sorry for the disturbance.
No, you don't need
Thank
to
you, sir.
worry.
Thank you.
And see, in that case, your F can be some function which can output a value between 0 to 1. And then you can threshold at 0.5. So it's like if it is greater than 0.5, obese, and if it is less than or equals to 0.5, maybe let's say not obese. Clear? So it would be like this. See, right now you take this as mathematics. Right now you take this as very simple mathematics, but the real-time example would be like this. Real-time example would be like this. So any regression problem, any classification problem which you have already studied, I think this is maybe 7th day of your STTP. So
Yes,
you
sir.
have
I got it, sir.
yeah. So you have already studied many classification and regression algorithm, even maybe clustering algorithms. So they can be solved using artificial neural network. You can have artificial neural network which can do classification. You can have artificial neural network which can do regression. You can have artificial neural network which can do clustering. So any problem could be solve. So these inputs are actually features of the inputs. This P1 to PR are features of the input, and A is your final signal. In case of classification, it would be class number maybe. In case of regression, it would be regress value, maybe selling price of the house. Would be like that. Yeah, so it would be like this. So you can see that over here we are using multiple actual inputs. Over here we are using multiple actual inputs. This is still a special input. This is still a special input. So basically, what is the difference between this slide and previous slide? In this slide, there was only one actual input. This is always a special input. In this slide, there are multiple actual inputs. So basically, this kind of artificial neuron can support r-dimensional input data. Can support r-dimensional input data. So it would be like this. And see, I'm giving the examples of activation functions now. So these are not the only possible activation functions. So it's like your activation function can be linear. So you know that if your activation function is linear, whatever is the net input would be the output. Whatever is the net input would be the output. And your activation function can also be a step function. F. Activation function means F. We have this F. So I said that there are quite a few options over here. So it can be linear, and in that case, whatever is the net input would be the output. It can be a step function. So you can see the graph of step function. So in case of step function, if your net input is greater than or equals to theta, theta is some predefined threshold. If your net input is greater than or equals to theta, output would be gamma 1. So gamma 1 is again some predefined value. Otherwise, output would be gamma 2, which is again a predefined value. If you use this kind of activation function, you can understand that output would either be gamma 1 or gamma 2. Output would either be gamma 1 or gamma 2. And you decide whether it would be gamma 1 or gamma 2 based on this threshold theta, which is some predefined threshold. It can also be a ramp function. So if it is a ramp function, you can see that it is linear in some range, and after that it is constant. So it's like if net input increases or decreases within some range, your output would also increase or decrease. But after some time, if your net input keep on increasing, your output would become constant. And similarly over here, after some value, below some value, if your net input keeps on decreasing, still your output would remain minus gamma. So again, these are some predefined values: gamma, minus gamma, and theta. This is log sigmoid. Precisely, this is log sigmoid activation function. So you can see the graph of this. So you can see that output would always be between 0 to 1. It would be 0. It would be 0.5 when net input is 0. It would be 0.5 when net input is 0. When net input increases beyond 0.5, you can see that output also increases beyond 0.5. When net input increases beyond 0, the output also increases beyond 0.5. So initially it increases rapidly, but after some time the increase is very little. The increase is very little. Same is the case on the other end. You can see that as your net input becomes lesser than 0, initially your output decreases accordingly, but after some time the decrease becomes very small. Decrease becomes the amount by which it decreases becomes very small. So this is log sigmoid activation function. So if my function f is log sigmoid, if it is log sigmoid, then the equation of log sigmoid is this: f of x equals to 1 upon 1 plus e raised to minus x. This is the equation of this graph or log sigmoid activation function. F of x equals to 1 upon 1 plus e raised to minus x. F of x equals to 1 upon 1 plus e raised to minus x. So whatever is the input that is processed using this equation, and this value would always be between 0 and 1, as you can see in this graph. As you can see in this Uh, See, this is actually a ReLU activation function, which is very popular nowadays, specifically in deep neural networks. ReLU stands for rectified linear unit. So there, if your net input is 0 or positive, output would be net input itself. But if your net input is negative, output would be 0. Look at this. If your net input, so this is x-axis is net input, and this is your output. If your net input is 0 or positive, output would be net input itself. But if your net input is negative, output would be 0. You can understand this from here as well. So over here, xi is the net input. So if your net input is 0 or positive, output would be net input itself. Otherwise, output would be 0. Otherwise, output would be 0. So for negative values of the net input, for negative net input, output would be 0. So this is known as rectified linear unit. Now I'm not discussing this, but then there are improvements over ReLU, which are known as leaky ReLU, parameterized ReLU, then randomized leaky ReLU. This we typically discuss while discussing, vanishing gradient problem and deep neural networks. It's like ReLU has a problem called dead neurons. ReLU suffers from a problem called dead neurons. So therefore, leaky ReLU was thought of, then parameterized ReLU was thought of, and then randomized leaky ReLU was thought of. But that is, too much of detail for this class. And ReLU was thought of because log sigmoid has a problem called unstable gradient. Log sigmoid activation function has a problem called unstable gradient. So unstable gradient problem can be divided into two, vanishing gradient problem and exploding gradient problem. So unstable gradient problem means it can either be vanishing gradient problem or exploding gradient problem. You may not understand this. Please don't worry about it, because then there can be a separate class on it, separate discussion on it. But basically log sigmoid activation function suffers from something called unstable gradient problem, and then therefore ReLU became popular. But then it was realized that ReLU delays. It doesn't solve unstable gradient problem. It doesn't solve vanishing gradient problem. It can delay vanishing gradient problem, but then sometimes it can introduce a dead neuron problem. So how to deal with the dead neuron problem? So therefore leaky ReLU, parameterized ReLU, randomized leaky ReLU were thought of. Though I am not discussing any of this. But these are some choice for activation function. These are some choices for activation function. So we have seen artificial neuron with one actual input. We have seen artificial neuron with multiple actual input. But in both the cases, if you have noticed, you had only one artificial neuron. Over here as well, you had only one artificial neuron. So who says that you can use only one artificial neuron? You can use more than one artificial neurons as well. So this is the case. Over here, you can see that there are basically this is artificial neuron 1, artificial neuron 2, and then you can see this dot dot dot, and this is S-th. This is basically S-th artificial neuron. So you can have any number of artificial neurons. You can use any number of artificial neurons. It's like if you use one artificial neuron, you are taking service of only one processor. If you use 10 artificial neuron, you are taking service of 10 processors. So if you believe that your problem is much more complicated than can be solved by one artificial neuron, then you may try to use multiple artificial neuron, because each artificial neuron has its own processor. So if you use 10 artificial neurons, 10 processors can work together and can solve your complex problem, which let's say may not be able to solve by one artificial neuron. So basically, you can use one artificial neuron with one actual input, one artificial neuron with multiple actual input, and multiple artificial neurons with multiple actual inputs. Like over here, this is artificial neuron 1. This is artificial neuron 2, and this is artificial neuron S. S can be any positive integer. So this is also fine. I'm not getting into too much details of this. Yeah. So we can have things like this. Now, before I proceed, if there is any doubt, please unmute and ask. Any doubt, don't worry. No question is a silly question. If there is any doubt, please ask. But please try to remember that the way I have introduced is this, that there was an artificial neuron with one actual input. There's one artificial neuron with one actual input. Then one artificial neuron with multiple actual inputs. And then I'm saying that you can also use multiple artificial neurons in a single layer. Multiple. So please recall that biological neurons are arranged into layered structure. So over here, S neurons are arranged into layers. So now this is multiple artificial neurons with multiple inputs. So see, we are making a gradual progression. One neuron, one actual input, one neuron, multiple actual input, and multiple neurons, multiple actual input. So we are making gradual progression. So this is perfectly fine. But right now, your multiple neurons are in a single layer. See, after this, if I take one step further, then you will again have multiple neurons, multiple inputs, but your multiple neurons now would be arranged into multiple layers. Right now, all these neurons are arranged into one layer. It's like this is your input, and these are 3 neurons, or let's say 4 neurons in this layer. So right now this is like this, right now this is like this, but you can have some other neurons in some other layer as well, maybe something like this, maybe something like this. So these are inputs. Okay, so 3 inputs. These are 4 neurons, 2 neuron, and 1 neuron. So this is basically 3, 4, 2, 1 ANN. 3, 4, 2, 1 ANN. That is, it can accept 3-dimensional input. There is one layer which has got 4 neurons into it. There is another layer after that which has got 2 neurons into it. And then there is the final layer which has got 1 neuron into it, who will take the responsibility for producing the final output. So this kind of neural network is known as 3-4-2-1 neural network. So you can create any kind of architecture. You can create any kind of architecture of your artificial neural network. You can create any kind of architecture of your artificial neural network. So this is basically next to this. That is multiple neurons in multiple layers. So one neuron, one actual input, one neuron, multiple actual input, multiple actual input, multiple neurons in single layer, and multiple input, multiple neurons in multiple layers. So that is the next stuff. I'll discuss more on this later on. Some of you may be having the query that how to decide basically that 3-4-2 when I said that any kind of architecture. So what do I mean by that? So I'll discuss this slightly later on when I'll talk about feed-forward neural network. But if there is any query, I'm waiting for a minute. You can raise your query before I proceed. I'm saying no query is a silly query, no question is a silly question. So please feel free to ask. So not bother. If you believe that you have not understood something, but you are the only one who have not understood that, then trust me, 50% are having the same feeling. 50% of the audience, 50% of the participants are having the same feeling. That's the fact. If you have not understood something, you are not the only one. There are 50% with you. So just go ahead and ask the question. Yeah, so I believe there is no question. So I hope the progression is now there in your mind. So keeping this in mind, I am introducing a concept called linear separability. I'm introducing a concept called linear separability. I'll be referring to this word many times. So you need to understand what do I mean by linear separability. And first of all, I'm discussing 1D case. I'm discussing 1D case. So let us assume that we have data of 7 students. We have data of 7 students. And we just have weight values of the 7 students. We just have weight values of these 7 students. So you can see 50. So this is weight of the first student, 55 weight of the second student, third student, fourth student, fifth, sixth, and seventh. So we have data of 7 students, and the data which we have is what is the weight of these students. And we also have this, that whether the student is obese or not obese. So this is like historical data, or the data you are already having, that this student 1 is not obese, student 2 is not obese, student 3 is not obese, student 4 is not obese, and the next 3 students are obese. So let's say 1D data we are having. Ideally, you should also have height values, but let's say we are not having height values, we are having just weight values. So now my question is this data linearly separable? So please understand, uh, each student belongs to one of the 2 classes. See over here, this is actually a classification problem, because you can see the student is denoted as either not obese or obese. Student is denoted either as not obese or obese. So this is actually a classification problem, rather binary classification problem. So the next question is the data of these 7 students linearly separable? So for that, so you know that we are having weight values. So let me have weight axis. Let me have weight axis. So let's say this is weight axis, and say this is 0. So this is 50. This is 50. This is 55, 60, 65, 70, 75, 80. This is my weight axis. And now what I'll do, let's say for not obese students, I'll use the symbol circle, and for obese students, I'll use the symbol cross to denote on this weight axis. So per student, weight is 50. So this is like a number line. This is like a number line. One axis means like a number line. The first student weight is 50. So he would be over here, and he is not obese. So for not obese, I said that we will use circle. So not obese. 55 not obese, circle. 60 not obese, circle. 65 not obese, circle. And next 3, 70, 75, and 80, they are obese, and we have planned to use cross. So cross, cross. So basically, I have plotted the data of 7 students on this weight axis. I have plotted the data of 7 students on the weight axis, and because the students were not obese, so I have used one symbol for them, and remaining 3 students were obese, so I have used another different symbol for them. Now, my question is, are these 7 data points linearly separable? Then the answer is yes. Why? Because see, you can figure out a line. You can figure out a line such that on one side of it, there are students or data points of one class, and on another side, there are students or data points of another class. It's like I can draw a line over here, maybe like this, or maybe like this. So there are quite a few lines possible. There are quite a few lines possible, but let's say if this is that line, then you can see that on the left of it you have only not obese, and on the right of it you have obese. Or maybe this line, then the same thing can be said. So if you can figure out such a line, if you can figure out such line, or let's say even point, if you can figure out such point or line such that on one side of it there are data points, students or examples of one class, and on another side there are students, data points or examples of another class, and those data points are linearly separable. So therefore these are linearly separable. The 7 data points are linearly separable. But let's say uh, if I take another example where we have 5 students, and again we are having weight values, again we are having weight values. So look at this. Over here, there is somebody whose weight is 60, and you know that person is obese. So this may be possible if person is very short. let's say person's height is just 4 feet 5 each, then maybe 60 kg, at 60 kg that person is overweight, obese. Okay? So because we are not having height value, we don't know why is it so, but maybe like that. So now look at another example where we have data of 5 students, and again we are having weight values of 5 students and whether they are obese or not obese. So again, if I draw the weight axis, this is again weight axis. So let's say this is 55, 60, 65, 70, 75, and again 55 is not obese, so circle. 60 is obese, so cross. 65 is not obese, so circle. 70 and 75 are obese, so crosses. So again, I have plotted data of 5 students on this weight axis. Again, I have plotted data of this 5 students, another 5 students on weight axis. This was data of some 7 students, and you could see that obese and non-obese could be separated by a line. Now, is this data linearly separable? Then you can see that this data is not linearly separable, because you can try to figure out any point or line. To try to figure out any point or line such that on one side of it there are examples of only one class, and on another side there are examples of only another class. Let's say if you try with this, let's say this is the point or this is the line, let's say, then you can see that on the right of it there are examples of only obese, but on the left of it there are examples of obese as well as not obese, not obese, not obese, and obese. Let's say you select this as the line, then on the left of it not obese, but on the right, on the, forget about this line now, this did not work. So let's check with this. So on the left of it not obese, but on the right of it obese as well as not obese. So if you can try with infinite number of lines over here, you can try with infinite number of lines over here, but no line, no point over here would be that special point or special line, such that on one side of it there are examples of only one class, and on another side there are examples of another class, only another class. So therefore this kind of data is known as linearly inseparable data. This kind of data is known as the linearly inseparable data. So we have discussed the concept of linear separability, linearly separable data and linearly inseparable data, and this is the example of 1D case. This is the example of 1D case. This is the example of a 2D case. So you can see that these 4 data points are belonging to one class because they have been indicated using this solid circle, and these 3 data points, they have been indicated using this standard circle, and you can figure out such line such that on one side of it there are solid circles and on another side there are this standard circles. So these 3 data points are belonging to one class, this 4 are belonging to another class, and you can figure out a special line. So therefore this 7 2D data points are linearly separable. Linearly separable. Same for the 3D. So in 1D it was about a special point, figure out a special point. In 2D it is about figuring out a special line, special line. So you understand the meaning of special now. Special means one side of it there are examples of one class, and on another side examples of another class. So in 1D it was about a special point, figure out a special point such that one side examples of one class, another side examples of another class, like this point. In 2D, figure out a special line. So in 3D, it is about figuring out a special plane. And in more than 3D, 4D and beyond, it is about figuring out a special hyperplane. It is about figuring out a special hyperplane. So if you can figure, let's say your data is 10D, your data is 10D, and if you can figure out a special hyperplane such that on one side of it there are examples of one class, and on another side there are examples of another class, then that hyperplane is a special hyperplane, and your data is linearly separable. Otherwise it is not linearly separable. So I hope you have understood this concept of linear separability. Again, I'm waiting for a minute. If there is any query, please unmute and ask. This is very important concept in artificial neural network and in general for machine learning. In general for machine learning, because there are some machine learning model which can work with only linearly separable data. If your data is not linearly separable, you need to augment those models with some additional techniques. So therefore, this concept is very important. If there is any doubt, please unmute and ask. Concept of linear separability. If your data points are 1D data points, then if you can figure out a special point, they are linearly separable. If your data points are 2D, then if you can figure out a special line, your data points are linearly separable. For 3D, it is about figuring out a special plane, and 4D and beyond, it is about figuring out a special hyperplane. And I explain what do I mean by special. One side, data points of one class, another side, data points of another class. At no side, there should be a mixture of data points belonging to different classes. So waiting for a minute. If there is any doubt, please unmute and yeah, at least someone can unmute and reply that there is no doubt, so that I can feel that I'm connected. So typically in class, what do I do is that I invite queries by unmuting or through chat window. And if there is no query, I ask them to write clear in the chat window. If you can do that, that would help me. It's like we feel more connected, isn't it? If there is any query, unmute and ask, or write in the chat window, or write clear in the chat window. That would be more than enough. So I can see clear and no queries from few.
Yeah, sir, you can go ahead, I think. There are no queries.
So let me take this further now. So now next, I am discussing perceptron. The next thing which I am discussing is perceptron. So now listen to me very carefully. A single perceptron. So perceptron, first of all, perceptron is artificial neuron only. Perceptron is actually kind of artificial neuron only. But in the strictest sense, perceptron is that artificial neuron which uses hard limit or hard limits as the activation function. See, this is in strictest sense, and earlier it was like this. Later on, perceptron word is used in more relaxed way. That is, now researchers are not binding like this, that perceptron's activation function should only be hard limit or hard limits. So it's like any other artificial neuron is also referred as perceptron now. But earlier, when all these things started, perceptron was an artificial neuron which can have hard limit or hard limits as the activation function. So hard limit is a function, hard limits is also a function. So there were only two options. But then later on, perceptron was used for artificial neuron with other activation functions as well, and that is the trend till date. That is the trend till date. But I'm talking about perceptron, and I'm referring perceptron right now in the strictest sense. That is, perceptron is an artificial neuron whose activation function is hard limit or hard limits. Whose activation function is hard limit or hard limits. Again, I repeat, this is in the strictest sense. Now, what it can do? A single perceptron can do binary linear classification. A single perceptron can do binary linear classification. You know binary classification. Binary classification means if your data points belong to two class, and figuring out that which data point belongs to which class, is known as binary classification. In binary classification, there are only two predefined classes, like person is obese or not obese. Whether student is obese or not obese is binary classification problem. But whether student is underweight, overweight, or perfectly weight is not a binary classification problem, because there you have three classes. The binary classification problem is the classification problem where you have only two classes. So I just told you that a single perceptron can do binary linear classification. That is, if data points are linearly separable, then for those and if those data points belong to only two classes, if data points are linearly separable, and if those data point belongs to only two classes, then single perceptron can learn to correctly classify them. If your data points are linearly separable and belong to only two classes, then you don't need anything more than a single perceptron. Just a single perceptron can learn to classify them. So please understand, a single perceptron can do binary linear classification. I just explained what do I mean by that. It can do binary classification on linear data, linearly separable data, and I have just explained what do I mean by linear separability. And your data can be n-dimensional. That's not an issue at all. Your data can be n-dimensional. N can be any positive integer. N can be any positive integer. So dimensionality of the input is not an issue. Dimensionality of the input is not at all an issue. The only thing is that your data points must belong to two classes and they must be linearly separable. Then a single perceptron can learn to do this classification correctly. You can train a single perceptron to do this classification correctly. So this is perceptron. So you can see that it is very similar to artificial neuron with multiple actual inputs. But look at this. Look at this. F is hard limit activation function. Now your F is hard limit activation function. And what is hard limit activation function? If net input is 0 or positive, output is 1. Otherwise, output is 0. So this is not ReLU. In ReLU, if net input is 0 or positive, output was net input itself, not 1. This was same, that if it is negative, output was 0. So hard limit activation function means if net input is 0 or positive, net input is 0 or positive, output would be 1. Otherwise, output would be 0. So A can either be 1 or 0. It would be 1 when n is greater than or equals to 0. And it would be 0 when n is less than 0. So this is hard limit activation function. So I said that this is perceptron in a strictest sense. Okay. And I told you that what perceptron, single perceptron can do? It can do binary linear classification. Two class, that is binary linear classification. It can solve binary linear classification problem. How it can do it? So you know that classification is supervised learning, and supervised learning is learning by presentation or learning by presentation of examples or learning by presentation of input output pairs. So it's like you may have data like this: height, weight, and let's say obese. So let's say height is 170, weight is 65, so not obese, so 0. Let's say height is 180, 70, not obese, so 0. This is 0, 0. Same. Let's say height is 160, weight is 80. So now this is obese, so let's say 1. Okay, obese. Maybe 150, 75, 1. So you may have data like this. You may have data like this. And so you can, first of all, you can see this. First of all, you can see this, that your data points belong to only two classes. The data point belongs to only two classes. Class can either be 0 or 1, means not obese or obese. And I'm not plotting these data points. I'm not plotting these data points, but let me assume that these data points are linearly separable. That is, you can figure out a line such that these two data points would be on one side of the line and this two would be on another side of the line. See, I don't know whether they are linearly separable. I've just randomly picked these values. So you can actually check it out by plotting it. But for simplicity, I am assuming that these 4 data points are linearly separable. That is, these 2 which are belonging to not OBs and these 2 which are belonging to OBs, they are linearly separable. That is, when you plot these 4 data points, you can figure out a line such that this 2 would be on one side of the line and this 2 would be on another side of the line. So binary classification problem, and I am assuming that they are linearly separable, then single perceptron can solve this problem. And in that case, this P1 to PR would be limited to only P1 and P2, because your input is described using only 2 features, height of the student and weight of the student. So you would just have P1 to P2. So you won't have this. You won't have this. And your desired output for this, and I just told you that supervised learning classification is supervised learning algorithm. And in supervised learning, we learn the machine learning model by presentation of input-output pairs, by presentation of examples. So your first input-output pair is 170, 65, and 0. It's like as P1, you will present 170, and as P2, you will present 65. And you will say that the target for this input 170, 65 would be 0. Target is 0, because you can see that over here it is 0. This is your training set. This is your training set. So supervised learning by presentation of input output pairs. So my input is 170, 65. So P1 is 170, P2 is 65. And what is the target? 0. So target is 0. So I'm presenting this 170, 65. See, initially these weights and biases would be random. Initially these weights and biases are random. So basically 170 into random weight plus 65 into random weight plus 1 into random bias. You will get net input. If this net input is, let's say this net input is negative. Let's say this net input is negative, or let's say this net input is positive. So if net input is positive, what would be A? If net input is positive, output would be 1. So it would output 1. It would output 1. What was the target? Target for 170 and 65? 0. So there is an error, because your actual output is not same as the target output. So you say that error is target minus actual. So target was 0 and actual was 1. Error is minus 1. So this error we would use to update weights and biases. So it's like we are telling to weights and biases that you are random, and because you are random, the actual output is not matching to the target output. So you look at this error and try to update yourself. You look at this error and try to update yourself so that this error is minimized, or there is no error, or there is no error. So basically we use perceptron learning rule to update weights and biases. And perceptron learning rule is this: new weight is old weight plus eta into E into P. Eta is the learning rate, at what speed you want to learn. You should not learn very fast. You should not learn very slowly. If you learn very fast, Pallavi is asking something, but I'm let me complete, then I'll answer. So you should not learn very fast. You should not learn very slowly. If you learn very fast, then you may not be able to reach to optimal answer. If you learn very slow, then a lot of time would be unnecessarily wasted. E is the error. I told you that E is the error, and it is calculated as target minus actual, and P is the corresponding input. It's like if I am trying to update W11, what is the input on W11? P1. So this would be P1. If I am trying to update W1R, what is the input on W1R? PR. So this would be PR. So this is the corresponding input on the weight you are trying to update. Similarly, bias is updated using this. B new is B old. New bias is old bias plus eta into E. Plus eta into E. So I hope you have understood the process. I'm talking about the process. It's like you picked up the first input output pair, 170, 65. You set the target to 0. Initially, these weights and biases were random. So using those random weights and biases, you calculated net input. I am assuming that the net input was positive and therefore actual output was 1, but target was 0, so they are not matching. There is an error. So therefore you will update all weights and biases using this rule. You will update all weights and biases using this rule. So weights and biases are updated because there was an error. Now what you would do, now you will pick up second input output pair. It's like now P1 would be set to 180 and P2 would be set to 70, and the target is still 0. Target is still 0 for this. So target is still 0. So this time this is P1 is 180, P2 is 70, and W or this weights and biases are updated. So P1, that is 180 into updated weight, this weight, plus P2, that is 70 into updated weight plus 1 into updated bias. You will get the net input. Let's say this time net input is negative. Let's say this time net input is negative. So actual output through hard limit transfer function, use this hard limit transfer function. If net input is negative, not greater than or equal to 0, output would be 0, means A would be 0. If net input is negative, output would be 0. Target was also 0. Target was also 0, so there is no error. So you don't need to update weight and biases. You don't need to update weight and biases. So for first presentation, the actual output was different than target output, so weights and biases were updated. For second presentation, actual output was same as target output, so weights and biases were not updated. Now you will set P1 to be 160. So now this time it will be set as 160, and this will be set to 80, and target would be set to 1. And again, it's like 160 into updated weight, means first time updated weight, because that is the latest weight. So 160 into latest weight plus 80 into latest weight plus 1 into latest bias would get you n, would get you n, n would get you a. Using this hard limit transfer function, you will compare a with target. If they are matching, you will not update weights and biases. If they are not matching, you will update weights and biases using these two equations. And these two equations are known as perceptron learning rule. So this is the process. This is the process. Then you will do it for the fourth input output pair. So you have only 4 input output pairs in the training set. So once you complete presentation of fourth input output pair, you can say that you have completed one epoch. You can say that you have completed one epoch or one set of iterations. One set of iterations. So it's like that. And typically you do multiple epochs. Typically you do multiple epochs. So when you should stop this? So one stopping condition can be fixed number of epochs. That is, you may say that we will do 5 epochs. That is, this 4 input output pairs would be presented 5 times. And so basically 20 presentations would happen. And maybe out of 20 presentation, maybe 15 times target and actual were not matching. So 15 times weights and biases would get updated. So your stopping condition can be fixed number of epochs, or it may be like in 2 consecutive epochs, if weights, none of the weights and bias changes, none of the weights and bias change, till you can stop. There are many other stopping conditions as well, but I'm not discussing all of them. So one of the stopping condition can be fixed number of epoch. Another stopping condition can be maybe like in 2 consecutive epochs, if weights and biases don't change, then still you can stop. So this is the process. This is the process. Now we will take numbers just to understand this. It's like a kind of numerical we will take just to make you understand more clearly. But I hope you have understood the process. You can see supervised learning, learning by presentation of examples. So you are learning this by presentation of examples, and learning neural network is learning optimal values of weights and biases. Is learning optimal values of weights and biases so that it can produce actual output which is same as target. So now let me take the query. Can we solve this problem using sigmoid function too? So you can definitely solve this problem using sigmoid function, Pallavi. But we are talking about perceptron and stochastic sense right now. We are talking about perceptron and stochastic sense. And if you remember, I told you that in stochastic sense, the activation function is hard limit or hard limits. So, and because we want to learn perceptron learning rule, because we want to learn perceptron learning. You can use feed-forward neural network, and there you can use sigmoid activation function along with gradient descent or backpropagation, and you can still solve the problem. But then you don't need to use such a heavy network. Since backpropagation is much complicated algorithm than this perceptron learning. So you know that your problem is binary classification problem, your data points are linearly separable, then there is no need of using any other sophisticated network. Please understand. I told you that single perceptron can do binary linear classification. So you know that your data points belong to only two classes. That is, your problem is binary classification problem. You also know that your data points are linearly separable. Then there is no need to use any sophisticated neural network. A single perceptron can do the job. Single perceptron can do the job. Obviously, a more complicated will also be able to do, but more complicated means more computation, means more resources would be used. If there is any doubt, again, I'm stopping for a minute. If there is any doubt, please ask. Or what we can do, I'm waiting for a minute and then we can break. Now, after break, we will see a numerical based on perceptron learning. And then we will start with multi-layer perceptron or feed-forward neural network. And there we will discuss backpropagation algorithm. So those kind of networks are used to solve problems which are non-linear in nature. But again, if there is any doubt, please unmute and ask, or write your query in the chat window, or please write clear in the chat window. So please do either of these two, means either you ask your query or write clear in the chat window. Yes, participants, I once again request, so I can see one clear. What about others? So means I'm requesting all the participants to unmute and ask if they have query or write clear. So all the participants can write clear if they have understood, so that we can break maybe for 10-15 minutes and then we can resume maybe at 11:40. So I can see quite a few clear now. So Dr. Surendra, are you there?
Yes, sir. We'll break for 10-15 minutes. So you.
Yeah, so we will resume at 11:40.
Okay, that.
And I'll mute myself and I'll come back in 10 minutes.
Yeah.
Yeah, thank you. Yes, shall we start?
Yes, sir, we can start, sir.
Yeah. Yeah, so before the break, we were discussing about perceptron learning rule. So now it's like we will try to solve a numerical so that you can practically understand it using perceptron learning rule. And please do not forget that a single perceptron can be used for binary linear classification. And in general, ANN in general, uh, because ANN means it encompasses all artificial neural networks. So ANN in general can be used to solve any classification, regression, or clustering problem. So any application, you think that it is a classification application or problem, clustering or regression problem that can be solved using artificial neural networks. Right now, we are talking about perceptron, a single perceptron, which can solve binary linear classification problem. So this is the data which is given to us. Assume 7 one-dimensional input patterns. So you have been given 7 one-dimensional input patterns. So basically 7 inputs are given and input dimensionality is just 1. Assume that the first 4 patterns belong to class 0. That is, first 4 are belonging to class 0 and remaining patterns belong to class 1. So remaining are belonging to class 1 with desired output 1. So basically you have been given training set like this. So you have input and then output. So input is 0.0. These inputs are given to you, one-dimensional inputs, 17.33.50, then 0.67, 0.83. You can see that they are given over here. So I'm just copying it over here. And 1.0. So these 7 one-dimensional inputs are given to you. And you have been told that the first 4 are belonging to class 0 with desired output 0. That is, for this, the desired output is 0, 0, 0, 0. And next 3, remaining 3 are belonging to class 1 with desired output 1, target or desired output 1. So this kind of data is given to you. So now the first thing is, uh, let's say you are thinking to solve this problem using single perceptron. Then you should do the condition checking. You know that single perceptron can be used to solve binary classification problem. Then you should ask that, is this a binary classification problem? Is this a binary classification problem? That is the first question you should ask. So you can see that your inputs are either belonging to class 0 or class 1. Your inputs are either belonging to class 0 or class 1. So means problem is binary classification problem. So first condition is met. What is the second condition? The second condition is that your data points must be linearly separable. So it's a binary classification problem, but that is not enough. For single perceptron to solve this problem, data points must also be linearly separable. So let us check that out. So let me draw this value axis. So your data points are just one value. So I'm drawing the value axis. And this is 0. This is 0.17, 0.33, 0.50, 0.67, 0.83, and let's say 1. And see, you have been told that first 4 are belonging to class 0. So let me denote them using circle. And remaining 3 are belonging to class 1. So let me denote them using crosses. So these 7 data points I have plotted on the value axis. Now question is, are these data points linearly separable? Then you can see that the answer is yes, because you can figure out a special point or line. You can figure out a special line such that on this side there are only class 0 data points, and on this side there are only class 1 data points. Class 0 data points on one side, class 1 data points on another side. Yeah, there is some noise in background because sanitization is going on. It will be over in a minute. Yeah. So you can see that these 7 data points are linearly separable as well. So now this is a binary classification problem, and data points are also linearly separable. Means single perceptron can solve this problem. So please understand, before we are planning to use single perceptron to solve this problem, we knew that single perceptron can solve binary classification problem. So we check that is it a binary classification problem? Answer is yes. Are the data points linearly separable? Answer is yes. So now, as both the conditions are met, we are planning to use single perceptron to solve this problem. So let me draw the perceptron. So it's like you will have input uh, and you will have sigma. You will have sigma, and this is 1. You will get n, and then you will apply hard limit activation function, and you will get a. So input are this, you know that input 7 possible inputs. Now see in data, see design a perceptron to classify these patterns. You have been asked that you design a perceptron to classify these patterns, and before doing that you check that can you actually use one perceptron for doing this? Are both the conditions are satisfied or not? And you can see that both the conditions were satisfied, so you are going ahead and you are trying to design a perceptron to classify these patterns. Use perceptron learning rule, those two update rule which we had seen before the break. Assume learning rate equals to 0.1. So basically learning rate, which is eta, is 0.1. Initial weight and bias to be minus 0.36 and minus 0.1. So initial weight is minus 0.36. So W minus 0.36. So initial weight over here minus 0.36. And bias, so this is W. And bias, initial bias, it's minus 0.1. As you can see, this has been given to you. So computation for 2 epochs. So I told you that one epoch is one complete pass-through training set. So there are 7 input-output pairs in the training set. So 2 epochs means you will present this 7 input-output pair twice. So you are supposed to show computation for 2 epochs. So let us start with first epoch. So first epoch, I'll start with the first input-output pair. So first input-output pair is 0, 0. So means input is 0 and target is 0. So this is input and output means target. So input is 0 and target is 0. So let me compute n. So you know that n is W into input plus bias. So what is W? Initial weight, initial value of the weight is minus 0.36. Initially weights are random, you know that. So over here they have given these random values minus 0.36 into input. What is input? Right now we are presenting the first input output pair. So input is 0. So minus 0.36 into 0 plus 1 into bias. So 1 into bias, initial value of bias, random value of bias which is given to you is minus 0.1. So minus 0.1. So you know that this is minus 0.1. This would be 0 minus 0.1. So this is minus 0.1. So net input is minus 0.1. If net input is minus 0.1, what would be A? Implies that A is 0. A is 0. Please remember the hard limit transfer function. If net input is 0 or positive, then output would be 1, otherwise output would be 0. So over here, you can see that it is minus 0.1 means negative. So actual output is 0. What was the target output? Target output was also 0. So there is no error. So you don't need to update weights and biases. So this you have done. Now you do it for 0.17 and 0. Second input output pair, 0.17 and 0. So over here, because actual output and target output match, we did not update weight and biases. Now we are presenting second input output pair, which is 0.17 and 0. So 0.17. So 0.17 into minus 0.36. Minus 1 into B, which is minus 0.1. So minus 0.1. So you know that this quantity would be negative, and this is so this is plus minus 0.1. This is also negative. So negative plus negative would be negative. So this would be less than 0. Net input would be less than 0. I'm computing n, and therefore A would also be 0. I hope you have understood. I'm computing net input while I'm presenting 0.17 and 0 as the input output pair. So 0.17 into minus 0.36 plus 1 into minus 0.1. So minus 0.1. So this is negative, this is negative. The result would be less than 0, negative, and therefore A would also be 0. A you get after applying the hard limit transformation, hard limit activation function on n. What is the target? Target is also 0. Actual is also 0. So you don't need to update weights and biases. Then 0.50 and 0. Let us do it for 0.50 and 0. So again, net input. So this is 0.50, 0.5 minus 0.36 and plus minus 0.1. Again, this would be less than 0. Therefore, A is also 0. Therefore, A is also 0. Target is also 0. You can see that. I have forgotten 0.33. I have forgotten 0.33, but it would be same. I have forgotten for 0.330, but it would be same. So I have forgotten that over here, but it would be same. Even there, actual output would be 0 and target would be 0. So weights and biases would not be updated. Now let us do this for 0.61 and 1. So there, n 0.67 multiplied by minus 0.36 plus minus 0.1. Again, I am calculating net input. I am presenting this input output pair now. Fifth one, 0.67 and 1. So 0.67 into minus 0.36 plus 1 into minus 0.1. So minus 0.1. So this quantity would be negative, and therefore A, that is actual output, would be 0. What is the target output? 1. So target output is 1, actual output is 0. So they are not matching. They are not matching. So now weights and biases should be updated using perceptron learning rule. So for that you need to calculate E. So E is target minus actual. Target minus actual. So target was 1 and actual came up 0. So error is 1. Error is 1. So error has been calculated. Now using perceptron learning rule, you need to update weight and biases. So W new is W old plus eta E P. W old is minus 0.36. Eta learning rate has been given to you 0.1. E, we have just calculated E as target minus actual 1, and P means what is the input on this weight? Input on this weight, it is 0.67 right now. 0.67. So you can compute this. You can compute this, and you will get some value. That is the new value of the weight. So now you can see that weight has been changed. Similarly, you can compute new bias. So B new is B old plus eta E. So therefore, B old is minus 0.1 plus eta is 0.1, which is learning rate. It has been given to you, into E, which is 1. So this would be 0. New bias is 0. Minus 0.1 plus 0.1, it would be 0. So this is new bias. This is new bias. Similarly, you are getting new value of weight. Now for the sixth input output pair, which is 0.83 into 1, 0.83 multiplied by new weight, whatever new weight, plus 1 into new bias, which is 0. So you'll get net input. Again, you will get A from net input. Compare A with the target output. If they are same, don't update weights and biases. Otherwise, you update weights and biases using this perceptron learning rule. Then do it for seventh one. You know what to do. Once you complete for seventh one epoch is completed. Then start with second epoch. Then start with second epoch and present the first input output pair, second input output pair, and keep on doing. So you have been asked to show computation for 2 epochs. So you complete 2 epochs, and then whatever weights and biases are there, they are learned through 2 epochs of perceptron learning rule. So I told you that stopping condition can be fixed number of epochs as well. So over here they have asked to means this kind of numerical can be asked in the exam if you are teaching a neural network as the subject. So this is the numerical, so that you can actually understand the computation and you can actually implement. Now I think you can write a C or Python program. You can write a C or a Python program for doing binary linear classification. It is as easy as this. I don't think it would take more than 20-30 minutes if I ask you to implement perceptron for binary linear classification, because it is as easy as this. It is as easy as this. If there is any doubt, please unmute and ask. Otherwise, write clear in the chat. If there is any doubt, please unmute and ask. Otherwise, write clear in the chat window. Either of these two, please do it. I can see a couple of clears. What about others? We have almost 33 participants. So please understand, I am trying to make you understand the internal working of this ANN. See, many people would use libraries, maybe sklearn or any other library they are comfortable with, and will implement artificial neural network, but they don't understand what goes inside. So you should always understand what goes inside, how that library is implemented. So like, I don't think you should use library for implementing perceptron. You know the logic, and trust me, it won't take more than 20 to 30 minutes for implementing this. But you can implement if you know the internal. And even for backpropagation, I'll show you the internal. Just like if you would understand that, you would be able to implement that. However, that implementation, would can take 2 to 6 hours, depending upon how your implementation skills are. But implementing backpropagation without using any library is perfectly possible. So, but you need to understand the internal, that how does it work. Then you can. Yeah. So this is perceptron learning rule. So I told you that single perceptron can do binary linear classification. What about multi-class linear classification? Means, let's say your data points are linearly separable, but they belong to 3 different classes, or let's say 4 different classes. Then you can use multiple perceptrons. And you can use multiple perceptrons. So like this, you can see that over here, your input is 3-dimensional, and there are 4 perceptrons. There are 4 perceptrons. So a single perceptron can do binary linear classification. For multi-class linear classification, you need perceptrons equal to the number of classes. So there are 5 classes, but data points are linearly separable. Then you can use 5 perceptron in a single layer. 5 perceptron in a single layer to solve the problem. If there are 4 classes, but data points are belonging to 4 classes, but data points are linearly separable, then 4 perceptron in a single layer like this. 4 perceptron in a single layer can solve that problem. So multi-class linear classification problem, that is data points belonging to more than 2 classes. But if they are linearly separable, then still this problem can be solved using equal number of perceptrons as the number of classes in the same layer, in a single layer. So that is perfectly possible. So binary linear classification, only one perceptron is enough. For let's say n class linear classification, n perceptron in a single layer is enough. But if your data points are not linearly separable, your data points are linearly inseparable, it may be binary classification problem or multi-class classification problem. A single perceptron or multiple perceptron in a single layer will not be able to solve that problem. So please remember this. If your data points are linearly inseparable, they may belong to 2 classes or more than 2 classes, but a single perceptron or multiple perceptron in a single layer will not be able to solve that problem. If you have such problem, means binary or multi-class linearly inseparable classification problem, then you have to use multiple perceptrons in multiple layers. That is, you have to use multi-layer network. That is, you have to use multi-layer network, maybe like this. So look at this. You have input layer. So now, see, till this, it's like you have input layer and output layer. There was nothing in between. But multi-layer network, they have at least one hidden layer. Multi-layer network have one or more than one hidden layer. So hidden layers are layers between input and output layer. So like over here, you had input layer and you had output layer. But multi-layer networks are those networks where there is at least one hidden layer, like this. Look at this. This is input layer, this is output layer, and there is a layer in between. So see, input layer neurons are simply, their job is to pass whatever they receive from the input. But these are actual neurons. These are actual neurons. So you can see that it is in one, these two neurons are in one layer and this neuron is in another layer. So you are using multiple neurons or multiple perceptrons. You are using multiple neurons or multiple perceptrons, but not in a single layer. You are using them in multi-layer architecture. So this kind of network can solve, can handle linearly inseparable data. So please understand the progression again. Single perceptron, binary linear classification, n class, where n is let's say greater than 2, n class linear classification problem, n perceptrons in a single layer, but 2 or more than 2 classes linearly inseparable classification problem, then you have to use multi-layer network. That is network with at least one hidden layer. So this is the example of multi-layer feed-forward neural network. Multi-layer feed-forward neural network. It's a feed-forward neural network. So neuron in layer I, each neuron in layer I is connected to every neuron in layer I plus 1, as you can see. A neuron in layer I is connected to every neuron in layer I plus 1. Like this neuron is connected to every neuron in the next layer. This is also connected to every neuron in the next layer. This is also connected to every neuron in the next layer. Same is the case over here. This is connected to every neuron, although there is a single neuron, but the next layer. So this is multi-layer feed-forward neural network. So now you may be saying that how many hidden layers we should use. So as far as machine learning is concerned, or as far as neural network, apart from deep neural networks is concerned, one or two hidden layers are enough. But one or two is a hyperparameter. Whether to use one uh, hidden layer or two hidden layer is a hyperparameter. You can figure out the best choice using algorithms such as grid search. Then how many neurons in each of the hidden layers is also a hyperparameter. Again, that can be tuned using something called grid search. But basically, this is a multi-layer network where there is at least one hidden layer, and this kind of network can solve the problem with linearly inseparable data. So now we are on to this, that how you can solve problems which involves linearly inseparable data. So I just told you that there you need to use multi-layer network, means a network with at least one hidden layer. So so if you had seen a perceptron, they were using perceptron learning rule for updating weights and bias. If you had seen perceptron, they were using perceptron learning rule for updating weights and bias. This multi-layer network, they use a backpropagation, error backpropagation to update weights and bias. They use error backpropagation to update weights and bias. And please remember, they have bias over here, not shown over here, but they do have bias, these neurons. This is data 4, data 5, data 6. So they do have bias over here. So I told you that perceptron, they use perceptron learning rule to update weights and biases. While feed-forward neural network, multi-layer network, most of the multi-layer network, they use error backpropagation to learn optimal values of these weights and biases. And internally, in error backpropagation, you use something called gradient descent. I believe that during regression, gradient descent must have been discussed, because you can solve linear regression using gradient descent as well as normal equation method. But I believe that gradient descent basics must have been discussed there. And the fundamental equation of gradient descent is this: new value of the parameter is old value of the parameter minus eta times del E by del parameter. That is error gradient with respect to that parameter. This is known as error gradient. You know, gradient is partial derivative, so del E by del parameter. So this is error gradient with respect to that parameter. So parameter in artificial neural network, if you remember, I told you they are weights and biases. See, in machine learning, parameter and hyperparameter are two different terms. Hyperparameters are typically tuned using techniques such as grid search. They are not learnt, they are tuned, while parameters are learnt using learning algorithms like perceptron learning and backpropagation. So you should not get confused between parameter and hyperparameter. Hyperparameter is something like there are choices available and you should figure out the best choice. But parameters are learned through learning algorithms. So over here you can see that there are 11 parameters, 6 weights here, 2 weights here, so 8 weights and 3 biases. So like if you want to update W14, then backpropagation will use this equation. W14, new value of W14 is old value of W14 minus eta, which is learning rate, times del E by del W14. If you want to update W14, so new value of W14 is old value of W14 minus learning rate times del E by del W14. So you understand del E by del W14. Del E by del W14 is error gradient with respect to W14. Del E by del W14 is error gradient with respect to W14. So this is, I told you, the general equation is parameter is that parameter minus eta times del E by del that parameter, error gradient with respect to that parameter which you are trying to update. So this equation internally it basically uses. So we will see this algorithm. We will see this algorithm as we will go along. But any doubt, I am again pausing for a minute. If there is any doubt, please unmute and ask. Or you can write clear in the chat window. You should remember the progression that single perceptron for binary linear classification, n perceptrons in a single layer for multi-class linear classification, and binary or multi-class linearly inseparable classification, you need a multi-layer network. I can see one clear. What about other participants? See, I don't know the makeup of the participants. I don't know whether we have students or faculties. So I'm referring everyone by the name. So please allow me for that. I'm not attaching sir or madam behind. What about other participants? If there is a doubt, please unmute and ask. Otherwise, write here in the chat. Yes, I can see quite a few clear now. So let me proceed now. So I'm presenting you one example. So basically, in feed-forward neural network, you have a forward pass, like you had forward pass in perceptron as well. Forward pass means you give the input and produce the actual output, and backward pass means you use error to update weights and biases. So neural network basically they have two passes, forward pass and backward pass. So forward pass you give you present the input and you produce the actual output. Then you compare actual output with target output to calculate error, and then you use that error to update parameters. It is known as backward pass. So same is the case with multi-layer network. First we will go through forward pass, that is we will present input output pair. So through input we will calculate the actual output. We will compare the actual output with the target output, and we will backpropagate that error. By comparing, we will get the error. That error we will backpropagate using gradient descent, means using this equation. Using this equation. You also know one thing, that initially weights and biases are random. Initially, weights and biases are random. So again, you have theta 4. One, one, one. So initially weights and biases are random. So you can see that those random weights and biases are shown in this table. So theta 4, theta 5, theta 6 are biases. And I told you that there is no consistency as far as the notations is concerned. Over here, W14 is like neuron 1 to neuron 4. So it's fine. You should not get confused because of this. So this is the weight of the connection connecting neuron 1 and neuron 4. And over here, again, neurons are numbered linearly just to avoid or just for simplicity. So these are initial random weights and biases which are given to you. And see, input is x1, x2, x3. So first input output pair is 101 and class level, that is target, is 1. So basically 101 1 is your first input output pair. Over here I'll demonstrate using only one input output pair. Over here I'll demonstrate using only one input output pair. So 1 0 1 and 1, this is my first input output pair. This is input and this is the target output. So this is also given in this table, and target is 1, which is also given in this table. So it's like we are trying to learn a neural network for some classification problem where data points are not linearly separable. So you will have quite a few other tuples, means you will have quite a few other input output pairs, but I am demonstrating the processing for one input output pair. The processing would remain same for other input output pairs of the training set. So we are presenting 1 0 1, and see, let us assume something. See, these are neurons of input layer. Their job is to simply pass on whatever they receive. But these are neurons of hidden layer. This is neuron of output layer. So I'm assuming that their activation function is log sigmoid. Their activation function is log sigmoid. So neuron 4, 5, and 6, I'm assuming that their activation function is log sigmoid. And please recall, I told you that if f is log sigmoid, and if the input to f is net, then output would be 1 upon 1 plus e raised to minus net. E is constant, 2.7183. So if f is log sigmoid, then f of net is 1 upon 1 plus e raised to minus net. That is, f of x is equals to 1 upon 1 plus e raised to minus x. The log sigmoid activation function equation is this. So keeping this in mind, we are presenting 1 0 1, and our target is also 1. This is input output pair, learning by presentation of example, supervised learning by presentation of input output pair. So 1 0 1, this is my input, and target output is 1. So I'm presenting 1 0 1. So let us so now, by now I think you must have realized that we can imagine that any neuron is divided into two logical sections. Any neuron is divided into two logical sections. First logical section computes net input, and second logical section applies activation function on that net input. So any neuron, we can imagine that it is divided into two sections. First section computes net input, and second section applies activation function on the net input. So keeping that view in mind, let us do the forward pass. So we are presenting 101. So let us compute net input of neuron 4 first. So you know that neuron 4 would receive. So again, I am having this over here. You know that we have this. Okay. So net input would be x1 into w14, net input of neuron 4. That is net 4. X1 into w14 plus x2 into w24 plus x3 into w34 plus theta 4. This would be net input in terms of number because we have values for each of this. So x1 is 1 into w14. W14 is 0.2. So 1 into 0.2 is 0.2. You can see here. We are calculating net input of neuron 4 here 0.2 plus sigma. Net input function is sigma. So plus x2, which is 0, into w24, which is 0.4. 0 into 0.4 would be 0, plus x3 into w34. x3 is 1 into w34, which is minus 0.5. So 1 into minus 0.5 means minus 0.5. You can see that. Plus minus 0.5, that is minus 0.5. And plus 1 into theta 4. 1. There's a call in between, so I just want to confirm. Am I audible? Someone please reply.
Yes, sir.
So plus theta 4, which is minus 0.4, so minus 0.4. So you now sum all this, means we have done 1 into w14 plus 0 into w24 plus 1 into w34 plus theta 4. We have done it over here. So if you sum this, this is minus 0.7. So this is the net input. This is the net input. So first logical section of neuron 4 has done its task, has done its job of computing net input. Now second logical section of neuron 4 will apply activation function on this. Will apply activation function on the net input, and we are assuming that the activation function of neuron 4, 5, and 6 is log sigmoid. So what is net input? Minus 0.7. And if this is log sigmoid, if input is x, output would be 1 upon 1 plus e raised to minus x. So input is minus 0.7. Net input is minus 0.7. So output would be, so I am designating output as O4. I am designating output of neuron 4 as O4. So O4 would be 1 upon 1 plus e raised to minus net input. So 1 upon 1 plus e raised to minus net input. So minus 0.7. It is f of x is 1 upon 1 plus e raised to minus x. E raised to minus x. So x is minus 0.7. So minus 0.7 will be plus 0.7. So 1 upon 1 plus e raised to plus 0.7. We may use calculator. E is a constant, 2.7183, and you will get 0.332 as the answer. So O4 is 0.332. Now, we have computed net input of neuron 4 and output of neuron 4. Now neuron 5. So this will happen parallelly. This can happen parallelly. So again, you compute sigma and apply f. So over here it would be x1 into w15 plus x2 into w25 plus x3 into w35 plus theta 5. So let us compute that. So x1 means 1 into w15. So 1 into w15, which is minus 0.3. So 1 into minus 0.3 means minus 0.3. Then x2 means 0 into whatever. 0 into w25, but 0 into whatever would be 0. So 0. Plus x3 into w35. You can see that it propagates to neuron 5 on w35 on this edge whose weight is w35. So x3, which is 1 into w35, 1 into w35, 0.2. So 1 into 0.2 means 0.2. And then plus 1 into theta 5 plus 1 into theta 5. So theta 5 is 0.2, 0.2. So this is minus 0.3 plus 0.4 goes to 0.1. So this is the net input of neuron 5. You have just computed net input of neuron 5. Now you apply activation function on this net input. So again log sigmoid. So 1 upon 1 plus e raised to minus whatever is the net input. So 1 upon 1 plus e raised to minus net input is 0.1. So you use that and the answer is 0.5. So this is O5. Output of this is I am designating as O5. So O5 is 0.525. Now again you are at neurons. So you can see that we are doing forward propagation. It's like input is reached to so let us calculate again. Am I audible? There is someone is calling constantly. So sometimes it gets muted in WebEx. Therefore, I am asking. I hope I am audible.
Yes, sir. Yes, you are audible.
Yeah. Sometimes what happens in when there is a call, it gets disconnected. Yeah. So now let us calculate net input of neuron 6. So again, sigma NF. You know this. So what would be sigma over here? O4 into W46. Output of neuron 4, which is 0.332. We have just calculated output of neuron 4, 0.332 into W46. So 0.332 into minus 0.3. So you can see that minus 0.3 into 0.332 plus O5. We have just computed O5, output of neuron 5, 0.525 into W56. So 0.525, O5, 0.525 into W56 minus 0.2. So 0.525 plus minus 0.2. So minus 0.2, 0.525 plus theta 6, 1 into theta 6, which is 0.1. So 0.1. So again, use calculator. If you calculate this, this comes to minus 0.105. Again, we are assuming that the activation function of this is log sigmoid. So output of this, so if I designate this as T6 because it is target for neuron 6, A6, you apply activation function on this net input, which is minus 0.105. So 1 upon 1 plus e raised to minus whatever is the net input. So 1 upon 1 plus e raised to minus plus 0.105. And if you compute this, actual output is 0.474. That is O6 is 0.474. What was the target? 1. Target was 1. Our actual is 0.474. So there is an error. Error. So you calculate the error. Typically, over here, error is calculated T6 minus O6 square, or maybe 1/2 T6 minus O6 square. That's the way you calculate the error. Now, why we do that? Because this is convex in nature and all these things. I'm not discussing. This might have been discussed during linear regression, because I told you that linear regression can be solved using gradient descent. But it's fine. You may assume that error is calculated this way: 1/2 T6 minus O6 square. So you calculate the error. Now this error we will backpropagate. Like even in perceptron learning, we were using this error to update weights and biases. Over here, we will use backpropagation to update weights and biases. This error we will backpropagate to update weights and biases. So now, that's what we are trying to understand now. Backpropagation algorithm. So we have completed forward pass. Once you get A6 and you calculate error, you got A6 as 0.474 and you computed error as 1/2 T6 minus O6 square, that is 1 minus 0.474 square. Means forward pass is completed. Now backward pass, that is backpropagation. Error backpropagation will happen, in which these parameters will be updated. So, and there are 11 parameters in this neural network. There are 11 parameters in this neural network, 8 weights and 3 biases. So from this you have let's say O6 or A6, whatever you want to do. Let me give 1/2 as well. So 1/2 T6 minus O6. Wait. So now let us try to update weights and let us try to update parameters. So let's say we want to update theta 6. Theta 6 is also a parameter, 11 parameters. So theta 6 is also a parameter. And I told you that we do backpropagation using gradient descent. And the general equation of gradient descent, please recall. I told you that it is parameter equals to parameter minus eta times del E by del parameter. So keeping this in mind, theta 6, new value of theta 6 should be old value of theta 6 minus eta times del E by del theta 6. So in this way, you can calculate new value of the theta 6. See why we are updating these parameters, because see T6 was 1, but A6 or O6 came to 0.474. So they are not matching, so we have to update parameters. So theta 6 is equals to theta 6 minus eta times del E by del theta 6. See, you have existing value of theta 6. What is the existing value of theta 6? 0.1. So you already have that. So that this implies that theta 6 is equals to 0.1 minus eta. Eta is learning rate. Learning rate is also given to you. Let's say that given learning rate is 0.9. Just assuming this is also given to you times del E by del theta 6. So next. So theta 6 is equals to existing value of theta 6. So existing value of theta 6 is 0.1. So 0.1 minus eta. So I'm assuming that the learning rate is 0.9 multiplied by del E by del theta 6. So to get the new value, the only unknown quantity is this del E by del theta 6. So now you should focus. So let this be 1, and you should focus on getting this value, because once you get this value, you plug it over here, you will get the new value of theta 6. So focus on calculating del E by del theta 6, which is error gradient with respect to theta 6, which is error gradient with respect to theta 6. So you know that error is here, and this neuron 6 you calculated, it's like net 6. See over here, you calculated net 6, net input of neuron 6, and over here you calculated O6, output of neuron 6. So right, initially gradient is over here. Initially gradient is over here. You have completed forward pass, and now you will start the backward pass. So initially you are over here. Initially you are over here. So now I'll use the chain rule. So where are you initially? You are here. You are here. What is being done here? You compute O6 here. You know that you compute net 6 here, and then this apply F on net 6, and you get O6. So over here you compute O6. So therefore I'm writing it like this. So I am over here. So you compute O6 over here. So I'm saying del E by del O6. Del E by del O6. Then we backpropagate. And see, by backpropagating, we need to reach to theta 6. We need to reach to theta 6. So you know, in forward pass, it's like you computed net 6 and then you apply F onto it to calculate O6. So net 6 to O6, the path was net 6 to O6. In the backward direction, it will be from O6 to net 6. O6 to, see, exactly you will move in the reverse direction. Like in the forward pass, you calculated net 6 first, and then you could calculate O6. So now you are and O6 was the last thing you calculated. It's computed outside. So del E by del O6. So now in the exact backward direction, O6 was calculated using net 6. So just before O6, you calculated net 6. So del O6 by del net 6. Del O6 by del net 6. So you were over here. Now you have moved here. Del with respect to del net 6, and del net 6 is computed in the first logical section. So now you are here. Now how is net 6 computed? It was computed like O4 into W46 plus O5 into W56 plus 1 into theta 6. See, you need error gradient with respect to theta 6. So you need to ensure that error gradient reaches to theta 6. It backpropagates till theta 6. So you know that this is O4 into W46 plus O5 into W56 plus 1 into theta 6. So before net 6, who contributed to net 6? Theta 6. Who contributed to net 6. Theta 6 directly contributed to net 6, and you want to reach to theta 6. So therefore, del net 6 by del theta 6. Del net 6 by del theta 6. See, in school days, we were, so this is your chain rule. We were checking like this, that this gone, this gone. So what is left? Del E by del theta 6, which is del E by del theta 6. So this is chain rule. We studied this chain rule in the school days. But how I have tried to make you understand is like, we wanted to update theta 6, and the only unknown quantity is del E by del theta 6. So del E by del theta 6, I'm getting through the chain rule. So initially, I am at the outermost section, which is the second section of neuron 6. So therefore, del E by del O6, because in second section you compute O6. From there, you move to first section. There you compute net 6. There you compute net 6. So del O6 by del net 6. And net 6 to net 6, theta 6 directly computes. So del directly contributes. So del net 6 by del theta 6. So this is the chain rule. Now you know partial differentiation. These are all partial differentiation. So del E by del O6. So if I differentiate this with respect to O6, this is T6 minus O6 square. So you know that if I differentiate this with respect to O6, it would be, so this 1/2 will remain as it is. And then I am differentiating T6 minus O6 square with respect to O6. So what would happen? 2 would come in front. T6 minus O6 into del by del O6 of T6 minus O6. I hope you can recall school days calculus. It's like del by del x square is 2x, right? But del by del x minus 1 whole square. So it's like you do this 2x minus 1 into del by del x minus 1, because x minus 1 is not the standard quantity. So you have to use chain rule again. So del by del x minus 1. I hope you can recall this. Del by del x square is simply 2x, because x is a standard quantity. You are differentiating with respect to x. Over here, you have square, but and you are differentiating with respect to x. Then square of x minus 1. So x minus 1 is not standard quantity with respect to x. So therefore 2x minus 1 and then del by del x minus 1. So I have used the same concept over here, del E by del O6. So this 2 will come in front, 1 by 2 into 2 T6 minus O6. And I am differentiating with respect to O6, and T6 minus O6 is not standard quantity. So del by del O6 of T6 minus O6. Then del O6 by del net 6. Del O6 by del net 6. Now, please understand, O6 is f of net 6, and f is log sigmoid. F is log sigmoid. Now there is a result. There is a result which can be derived very trivially, that f is log sigmoid. If f is log sigmoid, then f dash, that is del f by del x, is f into 1 minus f. So this can be derived in 3 steps. I'm not deriving it, but what I'm saying is that if f is log sigmoid, then derivative of f, if f of net 6 in f of net 6, if f is log sigmoid, then its derivative with respect to net 6 would be f of net 6 into 1 minus f of net 6. F of net 6 into 1 minus f of net 6. So same is the case over here. See, O6 is f of net 6. O6 is the output of neuron 6. How do you compute? By applying activation function of on net 6. That is f of net 6. And f is log sigmoid. So you are differentiating f of net 6 with respect to net 6, where f is log sigmoid. So result would be f of net 6 into 1 minus f of net 6 into del net 6 by del theta 6. Del net 6 by del theta 6. Now what is net 6? You know that net 6 is O4 into W for 6 plus O5 into W5 6 plus 1 into theta 6, that is theta 6. This is net 6. So del net 6 by del theta 6, that is you are differentiating net 6 with respect to theta 6. Partial differentiating partially differentiating net 6 with respect to theta 6. So this would be 0 because we are doing partial differentiation. This would be 0 and this would be 1. 0, 0 plus 1. Differentiating this with respect to theta 6, this with respect to theta 6, and this with respect to theta 6. So 0 plus 0 plus 1 means this differentiation is 1. So into 1. So I hope you have understood this. So this is from the first differentiation. This is from the second differentiation, and this is the result into 1. This is the differentiation of del net 6 by del theta 6. So now please understand. So this 2 and 2 gone. You have T6 1. You have O6 0.474. You calculated O6, which came to 0.474. So it's like you have this. So 1 minus 0.474 into T6 minus O6. Del by del O6, T6 minus O6. So if you differentiate T6 minus O6 with respect to O6, it would be minus 1. Del by del T6 by del O6 would be 0. And del O6 by del O6 would be 1. So this is minus 1. Del by del O6 of T6 minus O6 would be minus 1. Into f of net 6. F of net 6 is O6 and O6 is 0.474. 0.474 into 1 minus f of net 6, which is again O6 0.474 into 1. So now you have all the values. So you just do this multiplication, you just do this calculation, you will have del E by del theta 6. You will have del E by del theta 6, which you plug here, and then you will get the new value of theta 6. You will get the new value of theta 6. So I hope this is clear. So see, we are doing error backpropagation. We are doing error backpropagation where we are using gradient descent actually. This is the equation of gradient descent. Now, if you want to see more, so see, if you refer literature, in most of the literature, they will give you the equation of backpropagation. They will not show you how those equations have been derived. So I never prefer those ways. You should know that how those equations have been derived. What is going in internally, that is very important. What is going in internally, that is very important, because if you understand that, then and then you will be able to contribute. If you are doing research or planning to do research, then you can only contribute when you know internals of the algorithms. So then you can have the idea that okay, something is not that good at this step, and you may be able to alter it. So knowing internals is very important. See, most of, unfortunately, most of these students are BTech students. They don't get into internals. Rather, they tend to use libraries. So you can definitely use libraries, but then it doesn't mean that you should not know the algorithm. You must know the algorithms from top to bottom. So again, this. So now let's say you want to update W46. You want to update W46. So you know that again, W46 is equals to W46 minus theta times del E by del W46. So again, the only unknown quantity is this del E by del W46. So if you want to calculate del E by del W46 again, this is error gradient with respect to W46. So del E, you are right now here. Error is calculated here, and error is calculated because of O6. Error is 1/2 T6 minus O6 square. Is 1/2 T6 minus O6 square. So you are in the outermost section, that is second section of outermost neuron, that is neuron 6. So del E by del W46. So this will be again outermost. Over here you compute O6. So del E by del O6. And again you move exactly in the reverse direction. So O6 was calculated using net 6. So from here you come here. Now del O6 by del O6 by del net 6. And you know that net 6 was computed using as O4 into W46 plus O5 into W56 plus 1 into theta 6. Previously, it was with respect to theta 6, del E by del theta 6. So from here we moved here. This time we need error gradient to reach to W46, and you know that W46 directly contributes to net 6. So net 6 is a function of W46. So you can write this. So you know how to do this differentiation. You know how to do this differentiation. You know how to do this differentiation. So in previous case we have done that. In previous case we have done that. So I'm not doing it. Now let's say for theta 4. First let me erase this. We have one more slide, I think. Erase this. So I'm not doing it for W46. I just show you that how you can do it. Yeah, now let's say you want to do it for W14. So you know this new value of W14 is old value of W14 minus theta times del E by del W14. So again, the only unknown quantity is del E by del W14 because you know existing value of W14 eta is 0.9. So del E by del W14. So del E by del W14 we are trying to do for that. So del E error is over here and error is computed as 1/2 T6 minus O6 square. So O6 is computed here. So again we will start it like that. We are back propagating. So you start back propagation from the outermost section, which is second section of neuron 6. Now O6 is computed using net 6. So from second section of neuron 6 to first section of neuron 6. So del O6 is computed using net 6. Now you know that you need to reach to W14. You need to reach to W14 and W14 contributes to net 4. Net 4 contributes to O4. So if you can reach to O4, then you can reach to net 4 and then you can reach to W14. So now the target should be, because if W14 can be is contributing to net 4, so can be reached through net 4 and net 4 contributes to O4, so can be reached through O4 and you know net 6, you know net 6, so it is O4 into W46. See, net 6, you know this O4, which is output of neuron 4, O4 O4 W46 plus O5 W56 plus theta 6. This is your net 6. So you can see that, see previously we were terminating at W46 or theta 6 because we were trying to update them. This time we are trying to update W14. So we need to ensure that the gradient reaches to W14, which can be reached via net 4, which can be reached via O4. And as such, net 6 is also a function of O4. So del net 6 by del O4. So now you have reached to second section of neuron 4. So like second section of neuron 6 to first section of neuron 6, first section of neuron 6 to second section of neuron 4, where you compute O4. So del net 6 by del O4. Second section of neuron 4 to first section of neuron 4, where you compute net 4. Now del O4 by del net. And now let us write net 4 as well. So net 4, you know that it is x1 into W14 plus x2 into W24 plus x3 into W34 plus theta 4. So this is net 4. So you can see that net 4 we are trying to reach to W14 and net 4 is a function of W14. So this is your chain rule. Again, you can use school days trick. This gone, this gone, this gone, this gone. Only this and this are left, which is equivalent to left hand side. So this is the chain rule. This is the chain rule. So again, if you do del E by del O6, so this is your E. So this 2 will come in front, this 2 will come in front. So 1 by 2 and 2 are gone, and you will have E6 minus O6 and then minus 1. This is 1/2 T6 minus O6 square. I am differentiating with respect to O6, so 2 will come in front. You will have T6 minus O6 and del by del O6 T6 minus O6, which will result into minus 1. So this is del E by del O6. Now del O6 by del net 6. Del O6 by del net 6. So you know that O6 is F net 6 and F is log sigmoid. So this would be F net 6 into 1 minus F net 6, that is O6, 1 minus O6 itself. I told you this, that this could be derived very trivially. That if F is log sigmoid, then F dash is F into 1 minus F. So over here, F O6 is F of net 6 and F is log sigmoid, and we are differentiating with respect to net 6 only. So F of net 6 into 1 minus F of net 6, and F of net 6 is O6 only. So O6 into 1 minus O. Now del net 6 by del O4. So net 6 is this. Partially differentiate this with respect to O4. So you will get W46 here. This would be 0, this would be 0. So W46 plus 0 plus 0. W46. So this is third quantity. Now del O4 by del net 4. Again, O4 is F of net 4. O4 is F of net 4, and O4 F of net 4 F is again activation function of neuron 4, which is again log sigmoid. So this would be again F of net 4 into 1 minus F of net 4, or in other words, O4 1 minus O4 into. So this is for the fourth quantity. Now del net 4 by del W14. Net 4 is this. I am partially differentiating this with respect to W14. So this would be X1 partial differentiation. So this would be 0. Differentiating net 4 with respect to W14. So X1 0 0 0. So X1 plus 0 plus 0 plus 0. So this would be just X1. Now see, you have all the values. T6 is 1. This is 0.474. Minus 1 is constant. This is again 0.474. 1 minus 0.474. W46 is given to you. You should keep on using the old value of W46. W46 is minus 0.3. It's like you will use new values in the next epoch together, simultaneous update. So you also have W46. O4 you have calculated in the forward pass, 0.332. It would be 0.332, 1 minus 0.332. X1 you already have 1. We are presenting 101, so where X1 is 1. So you can calculate del E by del W14, which you plug here, and you will get the new value of W14. So I hope you can understand that in this way you can update all the parameters. In this way you can update all the parameters. So now when you will present the second input output pair, you will use this updated weights and biases. And see, this is error backpropagation using stochastic gradient descent. This is error backpropagation using stochastic gradient descent. That is, we are updating weights and biases after presentation of each input output pair. After presentation of each input output pair in the training set. So this is error backpropagation using stochastic gradient descent. You can do backpropagation using batch gradient descent as well. So there it's like you will have training set, and let's say there are 10 input output pairs in the training set. So you will present the first input, and there would be target for the first input. So you will present the first input, you will calculate the actual output, you will compare it with the target, and you will calculate the error. You will calculate the error, but you will not backpropagate. You will not backpropagate. You will not update weights and biases. Rather, you will store this error. You will store this error temporarily. Now you will present the second input and the corresponding target. Second input would be, feed forwarded. The forward pass would happen with same weights and biases as were used for the first input output pair. So you will do the forward pass, you will calculate the actual output, you will compare it with the target output, you will calculate the error, you will store this error. Let's say this is error 2 because it is for the second input output pair presentation. Then you do this for a third input output pair, again using same weights and biases as you have used for first and second input output pair. Keep on doing this for all input output pairs of the training set. I am assuming 10 input output pairs in the training set. So keep on doing this for all 10 input output pairs. So you will get E1 to E10. E1 is the error while presenting first input output pair. E2 is the error while presenting second input output pair. Up to E10 is the error while presenting 10th input output pair. Then you calculate the mean error. Each error is a squared error or 1/2 squared error. Then you calculate mean error. Mean of the squared error means mean square error. Means mean square error. And then you backpropagate. So I hope you can see the difference. In this example, you backpropagated after presentation of only one input output pair. So this is stochastic gradient descent. While in batch gradient descent, it's like if there are 10 input output pairs in the training set, you will do the forward pass for all 10 input output pairs using same weights and biases. You will have 10 errors. You will calculate mean error and then you will backpropagate and you will update weights and biases. So if you are doing backpropagation using this batch gradient descent, in one epoch, weights and biases are updated only once. But if you do backpropagation using stochastic gradient descent, and if I assume that there are 10 input output pairs in the training set, your weights and biases would be updated 10 times. Your weights and biases would be updated 10 times because there you are not waiting. As soon as you present input output pair, as soon as you get error, you immediately backpropagate and update weights and biases. And then for the second input output pair, you use updated weights and biases. And again, you will get error, you will immediately backpropagate. And for the third input output pair presentation, you will again use latest weights and biases which you got after backpropagating the second error. So that is stochastic gradient descent. That is, you update weights and biases after presentation of each and every input output pair. While in batch, you update only after presenting all input output pairs of the training set. So there is only one update per epoch in batch gradient descent while you use backpropagation. But if you use stochastic gradient descent in backpropagation, the number of updates is equal to number of input output pairs in the training set. So these are two extremes. There is something in between which is known as mini batch gradient descent. Something in between which is known as mini batch gradient descent. So there it's like you divide your training set into mini batches and you need to fix the mini batch size, which is hyperparameter. So let's say if you fix mini batch size to be 5, if you fix mini batch size to 5, and there are 10 input output pairs in the training set. So what you will do, you will pick up the first input output pair, you will do the forward pass, you will calculate error even, and you will store. Second input output pair, error, store. Third, fourth, fifth, that is end of mini batch 1. I assume mini batch size to be 5. There are 10 training examples in the training set. So there would be 2 mini batches. First mini batch would have input output pair number 1 to 5. Second mini batch would have input output pair number 6 to 10. So you start with first mini batch and present first input output pair from the first mini batch. Calculate the error but do not backpropagate. Then present the second input output pair and use the same weights and bias for forward propagation. Calculate the error and store it. Third, fourth, fifth. So you will get 5 errors. Calculate the mean error and now backpropagate. So update weights and biases. Now you start with the second mini batch. So start with the first input output pair of the second mini batch. That is actually sixth input output pair. Start with the first input output pair of the second mini batch, which is actually sixth input output pair. Do the forward pass using updated weights and biases. You have updated weights and biases after first mini batch. So you do forward pass using updated weights and biases. Calculate the error but do not backpropagate, store it. Now second input output pair of the second mini batch, that is actually seventh input output pair overall. Do the forward pass using updated weights and biases which were updated after first mini batch. Calculate the error, store it. So in that way again you will get 5 errors. Again now you will calculate mean error, average error, and now you will backpropagate. So again, weights and biases are updated at the end of the second mini batch. So you can see that in this case, your weights and biases are updated twice. Or in other words, your weights and biases are updated number of training examples divided by mini batch size times. There were 10 training examples and mini batch size was 5, so 10 by 5, 2 times. So if there are, let's say, 100 input output pairs in the training set and mini batch size is 5, then 20 times your parameters would be updated in one epoch. So you can do backpropagation using stochastic gradient descent, where you update weights and biases for each input output pair presentation. You can do backpropagation using batch gradient descent, where you update weights and biases only once per epoch. And you can do backpropagation using mini batch gradient descent, where you update weights and biases number of input output pairs divided by mini batch size times. So 100 and mini batch size is 5, then 100 divided by 5 means 20 times. So this is actually backpropagation algorithm. So please notice that I have not presented you the equation directly. Rather, I focused on how these equations are derived. What is the actual concept? What is the internal working? That is what is my focus. So now, again, if there is any doubt, you can unmute and ask. If there is any doubt anywhere, you can unmute and ask. Yeah, Vaisali is asking how to decide a number of hidden layers, neurons in hidden layer. So Vaisali is a hyperparameter. It's a hyperparameter. How many hidden layers is a hyperparameter. Number of neurons in each of the hidden layers is also a hyperparameter. So in machine learning, there are methods available for tuning hyperparameters, for deciding values of hyperparameters. And one such method is grid search method, which is very popular method, but it's a separate topic. And it is not limited to artificial neural network. It is applicable to any machine learning model, and most machine learning model have one or more hyperparameters. So grid search can be used to tune hyperparameters of any machine learning technique. Vaisali, is this clear? So there is no clear-cut rule that this many hidden layers or this many neurons in the hidden layers. But again, if we limit ourselves to machine learning, means we are not getting into deep neural network, then typically one or two hidden layers are enough, because there is a paper in 80s, there is a research paper in 80s which has proved that any mathematical function can be approximated using a neural network with one or two hidden layers. So there is a paper in 80s that any mathematical function can be approximated using a neural network with one or two hidden layers. So as far as machine learning is concerned, you will find neural networks with one or two hidden layers. But then number of neurons in hidden layers, then you need to tune it. Yeah, any other question? Any other question from any other participant? So please do this at home. See, it's like I have done this on Blackboard or using this graphics tablet. So what you should do is like you draw the architecture of neural network and then try to backpropagate. See, I'm doing backpropagation. Doing backpropagation is calculating error gradient. The ultimate equation would remain this. Like if you want to update, let's say theta 4, so equation would be this: theta 4 equals to theta 4 minus eta times daily by del theta 4. And I just demonstrated how you can, use chain rule for calculating this error gradient. And you know partial differentiation from our college days. You know differentiation from school days. Partial differentiation, I think we studied in the first year of engineering. So it is as easy as this. It is as easy as this. Yes, Dr. Surendra. So I think I'm done from my end. I'm done from my end. See, next is like, what can I do? Next is actually, I can have two new neurons in the output layer, and I can show backpropagation, because two neurons means there will be two errors. So you will aggregate those errors and then you will backpropagate. So Mahesa is asking when will the network converge? So there are stopping conditions. If you remember, there are quite a few stopping conditions. I'll not tell you all, but it's like uh, uh, fixed number of epochs is one stopping condition. Second is no parameters changes in 2 consecutive iterations. You can stop. And if your gradient becomes 0, that is an indication that you have reached to error minimum. So these are some of the things you can use. But these are not the only stopping conditions. There are more than this, but I am not explaining all of them. Mahesa, clear? Yeah, see, actually, I have explained gradient descent. I have explained gradient descent, that is the standard learning algorithm, but then there are almost 10 different variations, almost 10 different variations of gradient descent. That is like you have gradient descent with momentum. Then there is something called adaptive gradient descent. So like, let's say in one version of gradient descent, you keep on using the same learning rate. You keep on using the same learning rate. While there are versions like adaptive gradient descent and others, where you use adaptive learning rate. You use adaptive learning rate. That is, if you are continuously moving in the same direction on the error curve, then you can keep on increasing the learning rate. See, error curve would be like this. It would be convex. If you are continuously moving in the same direction, you can increase the learning rate. Concepts are related to that, and momentum is also similar to this. But to make you understand clearly, it's like I need to get into math, where first of all I need to explain that this 1/2 E6 minus O6 square is a convex function. Then I need to explain steps of gradient descent. So and then I need to explain the equation of adaptive gradient descent and momentum gradient descent, and then need to relate that. You can see that if we are moving in this direction, the momentum will help us. So this slightly involved topic. It won't take it will take at least 30-40 minutes, and some preliminary knowledge as well.
Professor, I'm Dr. Trishla Devi. Hello.
Yes, ma'am. Yes, ma'am.
Yes, I have a clarification. Suppose we have multiple vectors using which we would like to apply backpropagation algorithm to train the network. How exactly we have to do that multi-vector training using backpropagation?
By means of multi-vector, about multiple.
Multi-vector means I have gone through your example and I could get it is using a single vector. We can feed the features in the input layer, and based on the estimation of error, we can back propagate and repeat until the error gets reduced. That is
So
using one vector. One vector I have understood. One feature vector.
1011
Yes, sir.
101 is one vector for you, na?
Yes, sir. Yes, sir. That is one vector. One. Suppose I'm doing a project where I'm doing something like a face recognition or something where we have multiple features of face.
So please, madam, please.
Sir. Yes, sir. Suppose I want to do it practically, like how exactly we have to go about.
So please understand, X1 is one feature, X2 is another feature, X3 is another feature.
Okay, sir.
So it's not one vector. It is, so let's say you have face image. So
Yes, sir.
if you're using traditional machine learning techniques and image processing technique, then
Yes,
you
sir.
will convert your face image into feature vector, and that feature
Okay.
vector will have 20 values.
Okay,
So
sir.
it's like
Okay.
you will have X1 to X20, because feature is ultimately some real value.
Yes,
Feature
sir.
is
Yes, sir.
ultimately real value. So your face image is converted into 20 real valued vector. So you will have X1 to X20.
Okay, so I have to make a single vector and then apply this algorithm. That is what I'm understanding.
As far as vanilla or conventional neural network is concerned,
Yes, sir.
must have heard about CNN.
Yes, sir. Yes, sir.
Convolutional neural network. So they don't require you to do feature engineering. You can directly feed image as an input.
Okay, sir. Okay. So all the pixels that are present in the image can be directly taken as features, and then we can apply them directly without any processing.
Yeah. So please understand. Let's say you have a 10 cross 10 image, which is very small, but just for an example, you have 10
Okay,
cross
sir.
10. There are 100 pixels.
Yes, sir.
So, like if you want to use vanilla neural network, what you can do is like those 100 pixels can be converted into a, let's say, a column vector.
Yes, sir.
But so and then you can use a network like this x1 to x100. But then what is the problem? The image has got special information. Special
Yes, sir.
dependency
Yes.
is very key image. So when you create feature vectors that way, you are losing lot of special information from the image. An image is
Image.
all about special information into it. So therefore,
Ne-
vanilla neural network
Yes,
were
sir.
not successful directly on the image data. So therefore, we were using image processing techniques and we were converting images into feature vectors,
Okay.
and then we
Okay.
were feeding images by means of feature vectors into vanilla neural network.
Okay, sir. Okay. Okay, sir. Thank you so much for the information. Thank you, sir.
Yes. Yeah, any other question?
Anybody? Any other question? I don't think that there are questions. Pallavi madam?
Yes, sir. Thank you, sir.
So one
for-
last thing, ma'am, before you conclude. One last thing.
Okay. Okay.
So see, today we have gone through backpropagation, and trust me, if you know this, then it's like 50% of machine learning and 50% of deep learning. Am I audible? Means I'm getting some error over here.
No, you are audible, sir. I have removed the access right. That's why probably.
Okay. So basically, what I'm saying is that if you know backpropagation algorithm, then it's like 50% of machine learning and 50% of deep learning, because most of this artificial neural network they use gradient descent for backpropagation, and that's what we have just discussed. So if you use a CNN, in CNN you do backpropagation. If you use RNN, LSTM, GRU, you do backpropagation through time, and you use the same algorithm, you use the same concept. So if you know this, it's like you would be able to derive equations for CNN as well. You will be able to derive equations for LSTM, RNN, GRU as well. The concept remains the same. So this is perhaps the most important concept of machine learning and deep learning. And never accept equations. Please never accept equations. Rather, try to figure out that how actually backpropagation is done rather than accepting the equations. Yeah, that's it. That's it from my answer.
Yes, sir. As you rightly said, the basic concepts and internal working is indeed important. So thank you very much, sir, for a very informative session on ANN and backpropagation. I'm sure the participants must have benefited from the session. Thank you so much, and please accept the virtual memento, sir. That was indeed a great session. Thank you.
Yeah, thanks a lot. Thanks a lot.
Thank you, everyone.
Yeah.
Thank
Yeah, so I'm ending the meeting. I hope that's fine.
Yes, sir. Yeah. Thank you very much. Thanks a lot.
Thanks a lot. Thanks a lot. Bye bye.
Okay. Participants, we will meet in the evening time, 5 o'clock with Rocky sir. Please join on time. He shares the collab notebook, you know very well, correct? So please join on time.